This is an introductory video for Chapter 18, Electrochemistry, and much of what's in this lecture is not in your book. It was covered in Oxidation Reduction Reactions, which I think was Chapter 4, but it was in 1211. But I think most of you are probably pretty rusty on that, so I prepared this kind of review of how to balance an electrochemical equation. So as a reminder, definitions of oxidation and reduction, that's what all electrochemical reactions have in common. And oxidation means the loss of electrons. And for example, if sodium metal gives up an electron and forms sodium cation, that is an example of oxidation. Reduction is the gain of electrons. So the nonmetals tend to gain electrons just as the metals tend to lose them. So chlorine, for example, can pick up an extra electron because it's electronegative, and that would be an example of reduction. How many people remember this is with this saying, Leo says Gur. That stands for lose electrons oxidized, gain electrons reduced. Leo says Gur. Okay, for short, you will hear chemists calling oxidation reduction reactions redox reactions, okay, just so that you're not thrown when you read that. And basically a redox reaction is any reaction in which electrons are transferred from one substance to another. There has to be an oxidation and a reduction in every redox reaction. You can't have one without the other. And a perfect example would be to form table salt from its elements. It's kind of easy to see it's a redox reaction because neither one of the reactants has any charge. They both have a charge of 0, and yet we know that the sodium in sodium chloride is +1 and the chlorine is -1. So we know there have been electrons transferred, and it's pretty easy to see that it's a redox reaction. Not all of them are going to be that easy to see. So now here's a play with words that tends to confuse people. An oxidizing agent, okay, now this changes the whole thing. An oxidizing agent is something that causes an oxidation. An oxidizing agent does not get oxidized itself. All right, it causes something else to get oxidized. Likewise, a reducing agent causes something else to get reduced. It does not get reduced itself. Okay, so don't get stumbled up by those words. So I hope this doesn't confuse you more, but the oxidizing agent actually gets reduced itself because it causes something else to get oxidized. If you think about that, it makes sense. I'm not going to push it too much. All right, so let's go to the next page. All right, so in order to balance an electrochemical reaction, there are several steps. It's not just a matter of balancing the atoms in a chemical equation, which is what the conventional way is. You also have to balance charge. So it can get really complicated, but I'm going to start out with some easy examples. And the first thing that you want to do to successfully balance an electrochemical reaction or a redox reaction is to separate that reaction into two half reactions. So you want to identify the oxidation half reaction and the reduction half reaction. In order to do that, you want to assign what we call oxidation numbers to every single element in the reaction, oxidation numbers. So in a few slides I'll go over that. But to give you the basic concept, if you have the same reaction I talked about before, formation of sodium chloride from the elements, and you were to break those into the oxidation and reduction half reaction, this one again is easy to see that sodium has given up an electron. What does it mean to lose an electron or give up electron? That means it's been oxidized. So sodium has been oxidized, okay? And chlorine has gained an electron. It's gone from a 0 charge to a minus charge. When you gain electrons, you get reduced. So chlorine has been reduced. Okay, so it was easy to see in this reaction that the oxidation half reaction is sodium and the reduction half reaction is chlorine. It won't always be so easy. All right, so I'm going to tell you the rules of assigning oxidation state to every single atom in a redox reaction. I want to emphasize, though, the oxidation states are bookkeeping. They are not real charges, okay? So they're just a way for us to keep track of what share of electrons atoms have in a compound, like how much of an electron hog they might be. And so it helps us decide whether electrons have been fully transferred from one atom to another. So here we go. There are a set of rules, and you probably want to jot those down and have them handy. If you have an ionic compound, the oxidation numbers or states are simply equal to the charges on the ions. Okay, so calcium ion, I should put here ion, calcium ion has a charge of +2, so that means its oxidation state is +2. So ions are easy. Chlorine ion has a charge of -1, so its oxidation state is -1. So that's rule number 1. Oxidate rule number 2, well, I'm calling it 1 here, I guess I'll leave the numbers. Oxidation numbers for elements are 0, okay, in their standard form. So if you have, let's just say silver by itself, reacting with chlorine, okay, that silver has an oxidation number of 0, and the chlorine is an element too. It's a diatomic element, but it's still an element, so its oxidation number would be 0. Let's see, I just talked about this on the last page. I got myself out of order. All right, so rule number 3. Fluorine is so extremely electronegative that the only oxidation number it will ever have is a -1, okay? It's a non-negotiating atom. It demands having a -1 charge and nothing else. You will notice as we get into this chapter that the other halogens, chlorine, bromine, etc., can have a -1, but they can also have oxidation numbers that are actually 0 or positive. It's really quite strange, but that is the case. Remember, oxidation numbers are not charges, okay? They're kind of a method to bookkeep. All right, onward with our rules. If you have a compound, so let's say H2O. I'm just going to write it out, HOH. And let's say you're assigning oxidation numbers to every atom. This rule says that when you get oxygen in a compound, okay, it is -2, okay, except if the compound is called a peroxide. So let me show you a peroxide. This is a peroxide, and all that means is there's an oxygen-oxygen bond, a single bond between 2 oxygen atoms. If you do have a peroxide, you're told it's a peroxide, the oxidation numbers are -1 instead of -2. But in 99% of the cases, it'll be -2. All right, so the next rule. Hydrogen is almost always +1. Okay, so in water, +1, +1. Okay, the only time there's an exception is if hydrogen is combined with a metal. So there is a compound that's called sodium hydride. And because metals demand on having a positive charge, that means that forces hydrogen, if it bonds with a metal, to have a -1, okay? But again, 99% of the time, hydrogen is going to be +1 in a compound. Okay, the last rule, the sum of all of the oxidation numbers in a particular compound must equal the charge of the compound. So, what is the overall charge of water, for example? It's 0. That means that when you add together all the oxidation numbers and the elements in water, they better add up to be 0. Okay, and in this case they do. That's just kind of a way to check yourself that you assigned oxidation numbers correctly. All right, so here's an example, potassium chromate, and let's kind of follow our rules. First, you ask yourself, are there any ions? Okay. Why, yes, this is actually an ionic compound because it starts with a metal. So that means the oxidation number of the ions are going to equal the charge. So potassium's in group 1. We know it has a charge of +1. Don't pay attention to the subscripts, like don't change the charge for the subscript. Just put whatever the charge for one atom is above it. Chromate. Okay, this is going to take a little bit more skill. I'm going to actually write that down here. And what we know about chromate to start off with is that its charge, its overall charge, is -2. And we know that because there are 2 potassiums with +1, so we know in order to balance out the charge, it has to have a -2. Or we also know it by looking it up in a table. So this whole compound has a charge of -2. So that means the oxidation numbers of each of the elements, chromine and oxygen, have to add up to -2. So we really don't know what chromium is. Chromium is a transition metal. Its charges can be all over the place. So I'm going to go ahead and start by assigning an oxidation number to oxygen. We learned in the rule on the last page that the vast majority of the time, oxygen has an oxidation number of -2. So I'm going to go ahead and assign it a -2. Now you have to figure out through simple math what oxidation number chromium must have in order for the overall charge of this to equal -2. So there are 4 oxygens. If each of them have an oxidation number of -2, that means that the oxygens contribute a -8 charge to this species. If the species were neutral overall, that would mean chromine is +8, right? 8 minus 8 is 0. However, this is not neutral. It has to maintain a charge of -2. So that means that chromine must have an oxidation number of +6. To check ourselves, we would put +6 minus 8 equals -2. Okay, that's exactly what it should be. So the oxidation numbers for chromate are +6 and -2. Remember, just put the oxidation number for one atom. All right, here's some practice for yourself. Go ahead and turn the video off for a couple of minutes and try to figure out what the oxidation numbers are for each of the atoms in here. Each of these that I've given you have an overall charge of 0. If there is a charge, I would always tell you. So with that in mind, assign oxidation numbers and then go to the next page and I'll work them out for you. All right, so if you remember the rules, one of them said that fluorine always, 100% of the time, has an oxidation number of -1. There are 3 fluorines, so altogether, fluorine contributes an oxidation state of -3. Since this phosphorus trifluoride has a 0 charge overall, so that means that the oxidation number of phosphorus must be +3. Okay? And here we go. The oxidation numbers is phosphorus is +3, fluorine is -1. Again, you just give the oxidation numbers for one of each of the atoms. All right, moving on to carbon monoxide. Use the rule that says oxygen has an oxidation number of -2. All right, so carbon, because this overall compound is neutral, must have an oxidation number of +2. All right, moving on to ammonium chloride. That is a salt, it's an ionic compound. So the first thing I do when I have an ionic compound is separate the ions. So we have ammonium ion, which has a charge of +1, chlorine, which has a charge of -1. Now to assign oxidation numbers, I'm going to say, okay, here's chlorine, that's easy, because it's an individual atom with a charge, and the charge equals the oxidation number. So chlorine in this compound has an oxidation number of -1. Ammonium overall has a charge of +1. but I have to assign oxidation numbers to the individual atoms. I know that hydrogen, the oxidation number is almost always +1. That was one of our rules. So I'm going to go ahead and write a +1 for hydrogen. There are 4 hydrogens in this compound, so hydrogen overall contributes +4. Overall, I need to end up with a charge of +1. That means nitrogen must have an oxidation number of -3, okay? Because -3 plus 4 is +1, and that matches with the overall charge, okay? Alrighty. So after you've assigned oxidation numbers to every single atom in the redox reaction, you look at the oxidation numbers and you determine which atoms, which elements have given up electrons from the reactant side to the product side, and which elements have accepted extra electrons going from the reactant side to the product side. And that is how you identify your half reactions. That is your oxidation half reaction and your reduction half reaction. So here's an example. I know that you could balance this combustion reaction normally just by balancing atoms. That won't always be the case for all redox reactions, but it turns out that combustion reactions are actually redox reactions too. Sometimes you get double classifications like that. So I just want to demonstrate how you would assign oxidation numbers and determine what's been oxidized and what's been reduced. So I'm going to go through and assign oxidation numbers as we just learned. So hydrogen is +1. Since there are 4 of them, it contributes a +4, which means carbon must have an oxidation number in methane of -4. Weird, huh? But that's the case. Oxygen is an element in its standard state, so it has an oxidation number of 0. For carbon dioxide, I'm going to give the oxygens a -2 oxidation number. Since there are 2 of them, oxygen contributes -4. So in this case, carbon has to have a +4 oxidation number. All right, so all we have left is water. And I'm going to start again, as like I usually do, by assigning an oxidation number to oxygen, a -2. And this works out great. And hydrogen was another rule, +1. There are 2 hydrogens, so it contributes +2. +2 minus 2 is 0. So I'm all set. Have all the oxidation numbers assigned. Now, which element or substance has been oxidized? What does oxidize mean? Lose electron. Okay. Which element has lost electrons? Remember that an electron has a negative charge. So if you lose an electron, that means it becomes more positive, right? A bigger number. So let's see, what happens to carbon? Carbon goes from a -4 charge to a +4 charge. How did it do that? It obviously changed oxidation numbers, so it's involved in the redox reaction. It would have had to have lost several electrons, okay, to go from a negative charge to a positive. So if it lost electrons, that means that CH4 has been oxidized, all right? It lost electrons. What has gained electrons? Well, let's see. Let's look at hydrogen. It goes from +1, but it's still +1 over in the product side. So hydrogen has not been oxidized or reduced. How about oxygen? Oxygen goes from a 0 oxidation charge to a -2 in both cases. So it has gained electrons to go from 0 to -2. So that means that oxygen has been reduced. Okay, so carbon has been oxidized and it turns into CO2, and oxygen has been reduced. Now you'll notice that oxygen shows up in 2 of the products. So a logical question would be, well, which one do I write down here? Well, what I usually do, and it works vast majority of the time, if not all the time, is the CO2 has already been accounted for. in the oxidation reaction, half reaction. So I'm going to take, everything has to be accounted for if you're going to end up with a balanced reaction. So I'm just going to include the H2O and not the CO2 in my reduction half reaction, and it will work out. So these are the two half reactions that you would have for this combustion reaction. All right, so what have we done so far? We have assigned oxidation numbers. We have determined what has been oxidized and what has been reduced. And we've written skeleton half reactions for the oxidation and reduction reactions. So now that you've done that, you want to balance each half reaction using the following rules. You want to start out by balancing elements just like you do in a regular chemical equation, except do not try to balance hydrogen and oxygen yet. Okay? Once you balance all the elements, then go ahead and balance oxygen. You do that by adding H2O as needed. And I know that seems pretty strange. It'll be more clear once you start, once you start practicing. But let's just, for an example, say that you have elemental magnesium and you have some skeleton reaction written out so that you make magnesium oxide. If this were a half reaction, you were attempting to balance the redox reaction, and you can see that the oxygens are not balanced on both sides. What you would do is you would add H2O to whatever side needs it so that you have the same number of oxygens on both sides. Now, if you had two oxygens, let's say on this side, you would have to add two water molecules on the other side to balance it. Okay? Once you've balanced oxygen, you can see that you've introduced an issue with the hydrogen, because if you're balancing oxygen with water, you're introducing more hydrogen atoms. So you, of course, need to balance hydrogens. How do you do that? You add H plus as needed to whatever side. So how many hydrogens have we ended up with on the reactant side? 2 times 2 is 4. There are 4 hydrogens. So you add 4 H plus to the other side so that you have 4 hydrogens on both sides. Okay. After you balance the atoms and oxygen and hydrogen, you balance the charges. There's something called conservation of charge, where the overall, now I'm not talking oxidation numbers anymore, I'm talking about real charges, where the overall charge on both sides of the reactions need to be equal to one another. So for example, in this made-up example, I have a charge of +4 because of the 4 hydrogen ions I've added to balance atoms. However, there's no charge over on the reactant side. So what I would do is I would add electrons to whatever side to make the overall charge the same on both sides of the arrow. Since I have a 0 charge on the reactant side, how do I get a 0 charge on the product side? I do that by adding 4 electrons, because each electron has a minus charge. If I add 4 electrons, it's like adding a -4 charge, okay? And that balances out the +4 charge for an overall charge of 0 on the product side. So now the two sides match with charges. So let's go ahead and work out some examples. Oh, yes, that's right. Okay, so another rule you want to jot down. When you're all done balancing atoms, oxygen, hydrogen, and charges, you remember you've got 2 half reactions. You may find that, let's say you had to add 2 electrons to one of the half reactions, but maybe you only had to add 1 electron to the other half reaction. You've got to make the number of electrons added to each half reaction the same. So if I had, for example, let's say my oxidation half reaction. Let's say that I had added 1 electron to balance it. And in my reduction half reaction, let's say that I had to add 2 electrons to balance it. All right. So before you combine the two half reactions, which is the ultimate step, you need to make the number of electrons transferred for the half reactions equal. How do you do that? You find the common factor. This one's easy. Multiply everything in the oxidation half reaction by 2. Okay, and now you have the number of electrons transferred the same. Let's go through the entire process following all of the steps. You will be given a typical, we call this skeleton equation, which means it's not balanced. So if you see the term skeleton equation, you need to balance it. Okay, we're going to assign oxidation numbers first. Copper's an element, so it's 0. Nitrate ion has an overall charge of -1. So I still need to figure out the individual oxidation numbers of the elements. I'm going to assign oxygen as -2. There are 3 oxygens, so I need to balance out a -6 charge. I'm going to give nitrogen a +5 because -6 plus 5 is -1, which is the overall charge. And let's see, copper is an ion here, so its oxidation number is the same as its charge. And nitrogen monoxide, I'm going to give oxygen a -2 oxidation state. This is a simple one, which means the nitrogen has to be +2. Good deal. Now we have to identify what has been oxidized and what's been reduced. Copper has gone from an oxidation state of 0 to +2. It's done that by losing 2 electrons. What does it mean to lose electron? It means you've been oxidized, Leo. All right, so let's see what else has changed. Oxygen hasn't changed, which is often the case. Nitrogen has gone from an oxidation number of +5 to an oxidation number of +2. It means it's gained 3 electrons, okay? So nitrogen has gained electrons, which means it's been reduced. Okay, so we've identified what's been oxidized, what's been reduced. We're going to write out the skeleton half reactions. Copper has been oxidized, and so the copper skeleton half reaction looks like this. Remember the steps. You balance the atoms first. They're already balanced. There is no oxygen or hydrogen to balance, but we do have to balance the charge. There's a +2 on the product side and a 0 on the reactant side. They've got to be the same on both sides. I can balance that out by adding 2 electrons, because now we have +2 minus 2 equals 0. Okay, so this is easy. We're going to start with the easy ones. This is a completely balanced oxidation half reaction. Now we have to go through and balance the reduction reaction, which involves the nitrate ion going to nitrogen monoxide. All right, so here we go. Here's the skeleton half reaction for the reduction. Okay, here are the steps we need to do. We need to let's see, balance all the atoms except for oxygen and hydrogen. Nitrogen's already balanced. So let's balance the oxygen. Do you remember how we balance oxygen? We do that by adding water. We need 2 more oxygens. We only have 1 on this side. So we're going to add 2 water molecules. Okay. Now we have 1, 2, 3, and 1, 2, 3 oxygens. Oxygens are balanced. After you balance oxygen, you need to balance hydrogen. I now have 4 hydrogens on the product side. So I'm going to add, I guess I should move down, shouldn't I? Here we go. I'm going to add 4 hydrogens to the reactant side. So now if you look at all the atoms, they're all balanced. So double check yourself, prove it to yourself, and I need to finally balance the charge. I have an overall charge of +4 minus 1 equals +3 on the reactant side, and a 0 charge on the product side. I need to use electrons to balance charge. Each electron has a minus charge. So I'm going to add 3 electrons to the reactant side. And then I'm going to check my charge again. I have -3 plus 4 minus 1 for an overall charge of 0 on the reactant side. So that's good. The product side is 0 also. Now I have my two balanced half reactions, and I need to make sure that the number of electrons that I've added to balance the charge is the same in each half reaction. It's not. So you need to find a common factor, lowest common factor, which is 6. So I need to multiply the first half reaction by 3, everything in it by 3, and the second half reaction by 2. All right, so in other words, it's going to be 3 copper gives 3 copper ion plus 6 electrons. So multiply every single thing by 3. And the second half reaction, multiply every single thing by 2. So again, I'll have 6 electrons. Notice the number of electrons is the same now. Okay, and that will give me 8 hydrogen ions and 2 nitrates. I'm still multiplying everything by 2. 2 nitrogen monoxide and 4 water. Okay, so now you've matched up electrons. Now you literally add the two reactions together. Okay, how I do that, just like Hess's law, if you remember that, is I add every single reactant up together from both half reactions. So 3 copper, 8 hydrogen. I've already canceled out my electrons. 2 nitrate. Okay, those are all of the reactants. And put your arrow and add together all of the products. We have 3 copper ion. What else is a product? 2 NO and 4 water. Really, I usually encourage you to write the electrons in that you're going to cancel out, just to show, kind of to show your work. But then, of course, once you add them together, anything that's exactly the same on both sides gets canceled out. So let me make a point here, because a lot of people get confused about this. The 2 coppers cannot be canceled out because one of them is copper neutral metal and the other is copper ion. So in order to cancel, they've got to be identical. Sometimes you'll end up with water on both sides, and you can combine those terms. All right, here we go. I promise this is the final step. All of the steps we went through that I just described are assuming that the reaction is in an acidic solution. And that's why we can add, when we're balancing hydrogen atoms, we can add hydrogen, H plus, to balance hydrogen atoms, because we know there is H plus handy in an acidic solution. So most of the redox reactions are in fact done in acid, but there are some that are in basic solution. Obviously in a basic solution there's not much hydrogen ion. Instead there's hydroxide. So we have to add one final step on to balancing a redox reaction when it is in basic solution. The first thing that I want to mention is you follow all of the steps, all of them, as for an acidic solution, okay, including using the H plus to balance hydrogen atoms. Then you add OH ions, you add as many OH ions as you have H plus ions in order to neutralize the H plus so that you end up with water. So I think I'm going to have to show you that before it makes a lot of sense. All right, so here's the reaction we just balanced in acidic solution. Let's say that the instructions had said to balance it as if it were in basic solution. Okay, so what we would have to do, we would do exactly what we've done so far, but we would add a step that says to add as many OH ions as you have H plus ions. Okay, so I'm going to show you how to do that. You start rewriting the equation, and whenever you see H plus, you add the same number of OH. However, you have to do that to both sides of the equation. We're running out of room here. All right. So when you do balance a redox reaction in basic solution, there's usually a lot more canceling out at the end. First, you want to combine if there are H pluses and OH on the same side, you want to combine those and make them into water. So instead of having individual H plus and O minus, I'm going to add 8 water. Look what that does now, though. Now I have water on both sides of the equation. So I'm going to combine them. So I'm going to subtract 4 waters from each side. So these go away. Water goes away on the product side. And this 8H2O gets reduced to 4H2O. Okay? So that's what you would do if you were to balance it in basic solution. So here's an example I want you to try on your own. Try to go through all of the steps, okay? So you want to assign oxidation numbers to every single atom. You want to identify the oxidation half reaction and the reduction half reaction. And then you want to balance atoms and charge. You want to make sure the number of electrons transferred in each half reaction are the same. And then you want to add them together. So go ahead and turn the video off for a few minutes, give it a try, and I will go through the answer on the next page. So here's the final answer, and man, if you got that on the first try, pat yourself on the back. That's huge. There's so many pitfalls. It's like a bunch of nitpicky math or something to get through one of these. But I'm going to kind of walk you through it. In case you didn't get that, don't feel bad, but check yourself, figure out what your errors are. This is a perfect example of you need to work like a whole page of these problems to really kind of work the kinks out. But as you can see, I've assigned oxidation numbers to everything. So check and make sure you did that right. And then I've identified what has been oxidized, and it is the carbon. So you kind of take the whole compound it's with. Carbon has gone from -2 to +4, which means it's lost 6. Well, each carbon has lost 3 electrons, I guess. In any case, it's been oxidized. And so here is the oxidation half reaction. Chromium is not involved in it, so leave it out. It simplifies life. What has been reduced? Chromium has gone from +6, each chromium ion on the reactant side, to +3 on the product side. So it has gained electrons and it's been reduced. And so the reduction half reaction is here. Now I think it's pretty straightforward. You want to balance your atoms first. So in the oxidation half reaction, you would balance carbon first. Then you look for oxygen. You have a total of 4 oxygen on the product side, okay? So you would need to, and only 1 oxygen on the reactant side. So you would need to add 3 water, okay? And then to balance hydrogen, let's see what we have so far. We have 6 hydrogen from the ethanol, plus 6 more hydrogen. So we have a total of 12 hydrogen on the reactant side. So we need to add plus 12 hydrogen. And all we need to do now is balance charge. We have no charge on the reactant side, and we have a plus 12 on the product side. So I need to add 12 electrons to cancel out the plus 12. All right. Carbon is disagreeing with me, I guess. Onward to the reduction half reaction. Start out by balancing the chromium. And then we're going to move to oxygen. We have 7 oxygen there, so I need to add 7 water molecules. And let's see, now I have 14 hydrogens on the product side, so I need to add 14 H plus. And now I need to balance charge. I've really crowded things here, sorry about that. Let's see, on the product side, we've got a +6 charge. On the reactant side, we have a, let's see, dichromate has a -2. And then we have +14 hydrogen. So we have a total of a +12 charge on the reactant side and a +6 on the product side. So we need to add 6 electrons. Subtract a charge of 6 to the reactant side. +6 electrons. Alrighty, so if you can make out my scribbles here, we are done, except the number of electrons in the 2 half reactions is different. I have added 6 electrons in the reduction half reaction and 12 on the oxidation. So I need to make those electrons equal, and I'm going to do that by multiplying the reduction half reaction by 2. So if you go through that, add those 2 half reactions together, this is what you get for your final balanced reaction. Here's a final problem for you to practice. And notice that I said balance it in basic solution, which means you go through all the same steps we just did. And at the very end, remember to add as many OH ions as you have H plus ions, and then combine those to make water. See if you can do that on your own. There will be a worksheet in the content folder. Please, please, please work a bunch of these, and don't get too frustrated if you make errors, because typically when I balance a redox reaction, I've got to do it over a few times because of errors, so it's pretty common. That's it for this introductory lecture.